Am I streaming? Looks like I am. Okay, so we're trying to figure out something fun to do, but let's get set up first. So over here, we'll pull up some music potentially. And it's kind of summary right now, so let's pull up something summary. This one is kind of nuts. Okay, so what are we doing? Well, we've got some coffee, good old afternoon coffee, and some good old sparkling water. And I'm essentially admitting that I have no hopes for this Julia package on central symbol algebras. So there's a couple things that we can do. One, I thought of some types of algorithms that we could think about that have to do with well, central symbol algebras and elliptic curves. So I should really start streaming with Firefox. Elliptic curves and central symbol algebras. So particularly, hey, wonder if that's because I'm searching from my own account. Norms and central symbol algebras. So there's been a few. This is kind of what I was more looking at though. Explicit and descent on elliptic curves algorithms. So there's some things that we can do that pertain to central symbol algebras with elliptic curves, specifically looking for elliptic curves that split given algebra. I haven't totally given up on the paper of Eric Brussel yet either, but it is like another huge thing that we have to kind of go into. In terms of design of like this package itself, so if we had a central symbol algebras package, then it would look pretty shoddy. at the moment. Like, you could, let's say, compute the index sometimes for algebras that are defined over some Henselian field extension, or if you had an algebra that you were looking at over, say, some function field over Q bar, then maybe we could say something about the index using this kind of setup from Eric Brussel, which we're not even sure if we could make into an algorithm at the moment. So that's still an option. But it's a little bit sad that there's no way immediately for us to just like input some central simple algebra, output its index. And I also, or its exponent, these things that you'd actually care about studying typically. So, these are things that it would be good for us to think about, I guess. This is kind of an interesting paper title, at least, and it had to do with something with elliptic curves. So, what is this about? Here we've got a central sum algebra over a number field. We study the question of which integers of k are reduced norms of integers of a. Integers of a is kind of an interesting one. Already, so maybe coming from some order. But we prove that if k contains an integer that is a reduced norm of an element of a, but not a reduced norm of an integer of a, then a is totally definite quaternion algebra over a totally real field. This isn't really in the direction of anything that I wanted to think about, so. This one was, though. So I've seen this series of papers from Cremona, Fisher, O'Neill, Simon, and Stoll. And basically, the idea in all of these papers is giving a way to describe this group, H1K EN torsion, using central simple algebras. Right, so here, this is a third in a series of papers in which we study the N-Selmer group, which is some group fitting into an extension of the Tate-Shafarevich group and torsion points by this kind of Mordell-Vey group. We take E of K mod N E of K. So having this representation of a kind of a genus 1 curve inside of some form of projective space allows for searching irrational points on the curve. Which in turn gives you points of the elliptic curve itself. Sure, but there's definitely usually considerably less points on the curve C, you'd think. And a first step towards doing higher descents. Further application is to the study of explicit counterexamples to the Hasse principle. Summer group is a subgroup of the Galois-Coulomb homology group H1K E join N, which parameterizes N coverings of E. N covering represents a summer group element if and only if C is everywhere locally soluble. So if it has a point over each of the completions for each of the say evaluations of K. In this case, it was shown by Castles that C admits a K rational divisor of degree N if it's fitting into this N-Selmer group. We can then use the complete linear system of this divisor to embed C as a genus 1 normal curve of degree N, at least when N is greater than 2. More precisely, Castles shows that S of N is contained in the kernel. So this S of N looks different from the Summer group. It's contained in the kernel of the obstruction map, going from H1 to the Brouwer group. Yeah, there's a specific map that they're talking about here, which there's a bunch of obstruction maps. So this one is probably like the base point that you use is the elliptic curve. You take the identity, and then you take the line model coming from like n times the identity. In the first paper of this series, we give a list of interpretations of this group and of the obstruction map. Then we showed how given an element to explicitly represent the obstruction as an element of the Brauer group, you can find a central symbol algebra A of dimension n squared over k by just writing down the structure constants for A. We call A the obstruction algebra. Yeah, it's kind of interesting, isn't it? And in the case when you have an element in the Selmer group, A is actually just the matrix algebra, huh? Assuming the existence of a black box to compute such an isomorphism explicitly. Process we call trivializing the obstruction algebra. Right, so I think I mentioned this yesterday that I think that's a hard problem. But I was saying it for projective space and Sever-Rao variety. We then outlined 3 algorithms to compute equations for the curve. These were called the Hesse-Pencil, the flex algebra, and the Segre embedding methods. In the second paper, we developed the Segre embedding method. In this paper, we are again concerned with the Segre embedding method. We give an outline of the work in the earlier papers, and then give further details of the algorithms. In particular, if we take k as q and n as 3, we explain our method for trivializing the obstruction algebra. See section 6 for inside the black box. Something that is disappointing in this case, although it still could be interesting. Something that's disappointing in this case is like, are these all over a number field, for example? Algorithms that happen for number fields using, for like central symbol algebras over number fields are not so interesting, right? Just because every algebra is cyclic and all algebras have the same period and index. So you'd think that probably there are algorithms to compute these things, but they're not like general or good. They're just specific to the setting. So what we want is something a little bit more general. If we're gonna keep on thinking about these algorithms for central symbol algebras. So returning to general N, we observe that this Selmer group looks like that. Whenever I have an inner coprime, sure. Yeah, so something that I think is interesting about the correspondence between central simple algebras and elliptic curves, or the relation between the two, is that, so in this case, the elliptic curves people had the idea that you could use central simple algebras to tell you something about elliptic curves. And that's maybe true. So, they were interested, it looks like, in like writing equations for curves, and then also trying to figure out what the structure of the rational points is, or R. I don't know what I said. But I'm kind of a little bit more interested in going the other way. So I think that elliptic curves are relatively computable. Although I know they're not perfectly computable. And it would be nice if we could somehow utilize some algorithms that are known for elliptic curves in order to figure out some things about Sebrey-Brauer varieties or about central symbol algebras. So let's try to figure out if we can get anything from this. So in sections 2.2 and 2.3, we recall the construction of an Italian algebra. And a certain homomorphism such that the Selmer group may be realized as a subgroup of this quotient. Elements represented by guys in this unit group, or as a subgroup of this. First, these works for any n greater than or equal to 2 and is better suited for the computation of the obstruction algebra and equations for C. The second only works for prime n, but is better suited to computing the Selmer group itself, and that the class group and unit calculations are more manageable. Okay, so I'm kind of curious. I'm a little bit curious. Let me just think for a moment. I mean, something that is interesting is the fact that this group, right? H1K E adjoin N. It is computable in some nice sense, in the fact that, like, if you we're looking at a finite level, so if you just took some Galois extension of the base field, not the whole absolute Galois group, then this set is some finite list of maps. And so if you wanted to determine exactly what the order of an element is, that should be possible. If you wanted to determine how many elements are in there, that should be possible. And all of that just from knowing, right, the structure of this n-torsion subgroup. And so, let's see. I wonder if there's a way. It would be interesting maybe to have some kind of algorithm that says, like, whether or not the Brauer class of an algebra is in the image of this kind of obstruction map. Would that be interesting? Like, if I gave you just some random central simple algebra, then could you determine if, and if I gave you a random elliptic curve, Then you pick an end. Can you determine if that algebra is in the image of this map? That would be kind of interesting. One thing that is known is like based off of kind of the structure of the elliptic curve and its end torsion point subgroup scheme, and also the Vey pairing on that end torsion subgroup scheme. The image of this map has some very specific properties. So I have a few questions for myself. I guess that the reason why, if you have an element coming from the Selmer group, you get something which is locally trivial like this. Right, that specifically is for number fields. So if your curve is locally soluble, then over the case of a number field, then the algebra would have to be locally soluble also. But because of the Albert-Brouwer-Hasse-Noether theorem, that means the algebra is just trivializable. It's split. So that is some thing that's not going to have any kind of generalization. Okay, so what do we do? Okay, so potentially we could compute the first Galois cohomology of this thing given field K, some Galois extension of K. There's a question about whether you can compute the Galois group of that extension, which, I mean, for number fields seems fine, but for arbitrary fields, I guess that's questionable. And then you'd want, essentially, maybe just from... I guess you could determine that by yourself. I mean, okay, so now I'm kind of curious about just what's in my paper. Specifically, trying to remember, these obstruction maps are quadratic. And I'm trying to think. I feel like I've already passed where we say that they're quadratic. So right here, right? So mixed structure maps are quadratic so long as you are using a symmetric line bundle. So you get this interesting property that given an element inside this Galois cohomology group, the obstruction map of M times that element is M squared times the obstruction. And it's kind of related to the Weil pairing in this way. This kind of looks like a this kind of looks like the polar form of a so right, I mean this is probably literally the relation, but when you have some bilinear form, you can get sorry, maybe I should say so when you have some bilinear form, taking just kind of the diagonal on that thing gives you a quadratic form, and vice versa. If you have a quadratic form, then you can get a bilinear form by taking this. So from taking 2, u and v, then you get q of u plus v minus q of u minus q of v. So this is like saying that the Weil pairing on this group, or kind of the map that you get to H2 here, it is like the polar of this quadratic map, which is the obstruction. I'm trying to think, does this mean that it's actually computable? The Weil pairing is computable. I mean, I guess if you just had some explicitly given to you pairing, then you could compute this H1 group. And you could say what the image is probably inside H2. If I have essential simple algebra, how would I get something which is slightly problematic is just you know, this is landing inside the Brouwer group. But that doesn't seem to be computable at all. And if we're working with central simple algebras, then what does it even mean to kind of relate these to the Brouwer group computationally? So we could ask, like, right, can we construct a 2 cocycle from a central simple algebra? And the answer is maybe. Maybe we do something like, I mean, if the algebra is a cross product, So let's just assume that we can go from like cross product to 2 cocycle. Then if we get that algorithm, then we can get a 2 cocycle for any central symbol algebra. It would terminate, but we just don't know how fast it would terminate just by taking higher and higher matrix algebras. And eventually there's a cross product, and then we can just use this algorithm. Okay, so how would we go from known cross product to 2 cocycle? There probably is somewhat of an algorithm. To this type of problem, just from, I think I remember proving this a few years ago. Specifically, what I can think is like if you have like a cyclic field extension inside of your algebra, so like a maximal cyclic subfield, then there's some way to get kind of a code generator that gives you a presentation of your algebra. From a presentation of the algebra like that, you'd think that you can get a 2 cocycle. So I think that the same is probably true here. So that was section 100. So something like this, right? So right, so the point is you have to do some Skolem-Noether thing. So if we know that there's some maximal subfield, which is Galois, then for every element of the Galois group, E over the base, we can technically find some guy that once we conjugate an element of E by this guy, we get kind of the Galois action. And this would allow us to construct a 2 cocycle. So the question would be, how do you algorithmically get the Skolem-Noether conjugate element? Wonder if we can look that up. Yeah, the question is, how do we construct the question is something like, how can we construct such a conjugate element? I don't think that the proof of this is constructible in any sort of way. So let's look at the choose a simple module M. Okay, already impossible. Right, so if we could choose a simple module, like if there was some algorithmic way to just choose a simple module for our central symbol algebra, we'd be done with a lot of these problems because we just directly compute the dimension of M, and then that gives us, in some way, the index of A. We take tensor powers, eventually we get the indices of all the higher tensor powers, and we'd find out what the exponent is too. Okay, so this end is a skew field. M has 2 module structures. Yeah, so let's see. Algorithmic skull unearther. What is this? The isomorphism problem means to decide if two given finite dimensional simple algebras with center K are K-isomorphic, and if so, to construct a K-isomorphism between them. Applications lie in computational aspects of representation theory, algebraic geometry, and Brauer group theory. The paper presents an algorithm for cyclic algebras that reduces the isomorphism problem to field theory, and thus provides a solution if certain field theoretic problems, including norm equations, can be solved. This is satisfied over a number of fields. It's probably relatively close to one of the only places that you can solve certain norm equations. As an application, we can compute all automorphisms of any given cyclic algebra over a number field. A detailed example is provided, which leads to the construction of an explicit non-cross product division algebra. It's kind of interesting. So what is the... I'm actually really interested in this paper, suddenly. So there are several applications, for instance, to compute the irreducible representations. When was this posted, by the way? 2007? For instance, to compute the irreducible representations K for a finite group G, not divisible with the characteristic, one can decompose a semi-simple group ring into its simple components and then solve the splitting problem for each component. This is actually probably a big reason why a lot of this stuff is going to be totally intractable. Just because if you can say anything about simple algebras, then you'll be able to say something about representation theory of finite groups. Hey, Chacho. You getting up on the desk? Yeah. Whoa. Alright, we don't need the keyboard for a little bit, so Chacho can lay down. Chach. Okay. So, let's see. But the splitting problem also occurs if one wants to compute orthogonal idempotent generators in central simple algebras. So this was something that I did want to do. All of this is something that I want to do. But I don't really think it's super reasonable to try to do it. And I kind of think that this over a number field is maybe like one of the few places that you'd actually be able to do it. Which apparently this paper is saying that you can. And I think I kind of knew that it was around. So in this paper, we pursue an application that is motivated by explicit algebra constructions. Because various constructions make use of automorphisms of simple algebras that are non-trivial on the center, we study the problem extending automorphism of the field to an automorphism of the central simple K algebra and show that it reduces to the isomorphism problem. That's believable. This is kind of saying... Actually, I don't know quite what this setting is. Is that something like automorphism of K? Yeah, why would this actually make use of an automorphism which is non-trivial on the center? Unless you have to like first split the algebra in order to consider automorphisms. I'm not sure. The present paper solves the isomorphism problem for algebras that are presented as cyclic algebras. Okay. I'm not opposed to just thinking about these ones only. These are like the easiest ones to construct realistically. So that's why there's a whole symbol algebra constructor in the Julia package. Cyclic algebra is blah. Central symbol algebra that contains maximal subfield, which is cyclic over the center. This is an okay way to say this, but I don't even know if it's the Megami. Climbing up on my chest. Yeah, you trying to hang out too? So we say an algebra is presented as, I mean, I was just thinking because maximal subfield is not the most general way of saying cyclic algebras. Cyclic algebras can exist even. I would say that cyclic algebras are kind of like, I mean, there's such a thing as a Galois algebra, and there's a cyclic algebra, which is not a field. It's kind of a more general notion. Okay, anyways, so we say an algebra is presented as a cyclic algebra if a cyclic maximal subfield is explicitly given. For example, this can be a presentation by structure constants plus an explicit generator of a cyclic maximal subfield, having only the theoretical information that the algebra is cyclic. For example, if the center is a global field, is not sufficient. Right, so that's like if we had just a specific symbol algebra, but not if we have like tensor products and then we don't know what a generator would be. There's no algorithm available that can produce cyclic maximal subfields of central symbol algebras except for certain small degrees. I mean, over a number field, if you knew that you had a division algebra, and I want to say almost even if you don't know if you have a division algebra, I feel like you just take some random element and let it generate a field, and then that's not going to be cyclic, is it? Yeah, that's just going to be some random field, probably. Wonder how many of those you have to try before you get a cyclic one. Okay, anyways. For quaternion algebras, it's trivial. Cubic algebras, one finds a cyclic maximal subfield simply by proceeding along the proof. Right, if you can find a cyclic maximal subfield, then if there's an algorithm, basically that means that all of them are cyclic. That makes a lot of sense. That's almost the best, yeah. That's almost the best argument that I've heard for why there's no cyclic degree 5 algebras. Or why there are, not that there are none, but why there are some that are not. The algorithms of this paper work by reducing the isomorphism problem to norm equations. Norm equations, right, must be impossible to solve also, generally. Right, norm equations are in general hard to solve, but algorithms are known over number fields, and of course over finite fields, sure. Using computer algebra systems for those norm equations, our algorithms actually become applicable over number fields and finite fields, but finite fields not interesting so much. Actually, probably over finite fields, doing some of this stuff actually is interesting. So, algorithm 1, splitting of cyclic algebra. Let A be a cyclic algebra of degree n. The splitting problem for A is solved as follows. Fix an embedding of L, the cyclic extension, into matrix algebra. It's not hard. You just take maybe like the polynomial that's giving you the cyclic extension and pick the companion matrix for that polynomial. That'll generate some cyclic extension inside the matrix algebra. Compute a matrix X such that inner automorphism of X restricted to psi of L is the conjugate. So this is the Skolem-Noether theorem, right? This is basically just doing exactly what I said, but I assume that there's some explanation, yeah, probably above that I skipped, that says how you do 2. Its computation is a linear problem. Is that believable? So psi, okay, so sigma is a linear map. Psi, sigma, psi inverse. You want an element X such that when you conjugate L, you get sigma. That's a linear problem. Right, so if I pick a basis, K basis for L, then I could say what sigma does to that K basis, presumably. And so I want a matrix such that conjugating my basis elements give me some new elements. I guess that might be a one thing that I have a hard problem believing is, like, let's say I have a general n by n matrix, right? And I take basis vectors for my L space. Feels like when I do, okay, we got cats on cats on cats. Feels like when I do, okay. We can all live together in harmony. Feels like when I do some conjugation, I should get something that's like higher order than linear, but maybe it's just linear. I didn't write it down. Kind of want to try though. So let's just do a little bit of a hand computation. So I've got some, let's say, basis element, which is some n by n matrix. I'm going to just do a 2 by 2 example. So A, B, C, D. Let's say that I have some involution, which is going to give me, fuck it, like minus A, minus D, B, C, and then let's do like E, F, G, H. E, F, G, H. So I can realize this as multiplication on left and right. And then I get something that's like, right, it's like EA plus FC is equal to minus AE plus BG. And I don't know E, F, or G. I know everything else though. I guess this is a linear equation, yeah. In terms of the things that I do know. And so if I do this for all of these guys, I'm just going to get some system of linear equations, yeah. And then I just have to solve for EF. Yeah, so Skoll-Noether problem is just a linear equation. Okay, great. Yeah, system of linear equations, yeah. Okay, so that is solvable. That means That means, what was I thinking about before? So for cyclic algebras, algebras presented as cyclic algebras, right? We could totally determine a 2 cocycle. Okay, this one is, at least for the splitting problem, I think this is not an easy thing. So solve the norm equation. The norm of x is equal to a over b. So you take generators, right, like a and b. So this is like just saying, like, let's just look at symbols a, b, and then see if I mean, I kind of want to say, like, yeah, I think there's another way to say this. Like, if you just had this realized as so if there were, like, enough roots of unity and you were looking at a symbol algebra, then you would just ask, is A a norm from the field generated by taking nth roots of B or something like that. I think this is maybe the more general way of saying it for cyclic algebra. If there's no solution, then A is not split. Otherwise, if there is a solution, A is split, right? Otherwise, size extended to a splitting from A to this matrix ring by mapping V. I'm kind of realizing that, oh yeah, V is probably just the, okay. The way that I usually write cyclic algebras, I would say you have L lower k, sigma, and then just a field element. And then you define, I guess V is maybe the basis element, so that V to the n is A. Is that true? Setting A to be V to the n, we denote this algebra, yeah. Okay. By mapping V to psi of x times x. Whoa. Hey, Megami. Caught me off guard, bud. Okay. Okay. Getting a little bit too close to the coffee, bud. Okay, I want to know if there was any other work published on this. So let's look up isomorphism problem. Go to MathSciNet. So kind of want to log into MathSciNet over here.
should just do another scene or something. I can just do math sign out here.
Okay, so the isomorphism. And can we just put this over into this window? For cyclic algebras. Timo, Hank? Relevance? Don't know why they don't sort by relevance, just straight up. Okay, we got 3 chances. And they're not looking like they're gonna solve the problem. So, explicit isomorphism quaternion algebras over quadratic global fields. The main results are corollary 4.6 and 4.9. So in this case of quaternion algebras over a function field, there exists a randomized polynomial time algorithm for determining an explicit isomorphism. That's kind of shocking, isn't it? In the number field case, there exists a polynomial time algorithm for determining an explicit isomorphism that is allowed to call an oracle for factoring integers. Okay, so I mean, so it's not actually polynomial time. While previous algorithms in the could solve this problem, such complexity could only be achieved in the case that the discriminant of k was bounded. The main idea was to replace search for an isomorphism by the search for a central symbol algebraic isomorphic, thus reducing the degree of the field. The step which uses code restrictions of algebras, it is exploited that C is of the form A tensor B op. Okay, I'm kind of curious. So, in 11 and infinitely in 30, an algorithm polynomial in log D was provided when A was isomorphic to M2. So if A splits over quadratic extension, a very fast algorithm was provided giving an explicit isomorphism. Case where K is a global function field. Where some authors proposed a randomized polynomial time algorithm. This algorithm is somewhat analogous to 24, but it is polynomial in the dimension of the matrix algebra. In this paper, we initiate a new method for dealing with field extensions, which is analogous to Galois descent. It is known that finding an explicit isomorphism between A and the matrix algebra is polynomial time equivalent to finding a rank 1 element in A. Which sounds hard as fuck, is my opinion. Right? I mean, this is like, I mean, even in the matrix algebra case, I think that's a hard problem. I asked this question, which is that if you have, say, like a finite set of matrices, then can you find an algorithm that determines the minimal rank of a element in the linear combinations of those matrices? And that's, I think, an NP hard problem or something like this. So one could find a subalgebra of A isomorphic to a matrix algebra, and one could apply the known algorithms for the subalgebra, and that would give an exponential speed up in both cases. I don't know what is insinuated there. So furthermore, these types of methods should work equally for the function field and the number field case. Lots of magma used today is what I'm seeing. Yeah, so it's a natural algorithmic problem to compute the structure of A, i.e. compute the Jacobson radical, compute the Wedderburn decomposition of A mod the radical, and finally compute an explicit isomorphism between the simple components and matrix algebras over some division algebras. Yeah, the problem has been studied for various fields, including finite fields, field of complex and real numbers. All of those are trivial. I mean, the real numbers is maybe not so trivial, but... global function fields and algebraic number fields. These are the only fields where it's like, you know, you have as much hands-on information as you can get. So there exists a polynomial time algorithm for computing the radical of A over any computable field. There also exist efficient algorithms for every task over finite fields in the field of real and complex numbers. Finally, for global fields, or field of rational functions over finite field, there exist sufficient algorithms for computing Wedderburn decompositions. Kind of curious what that means. So, does that mean finding idempodes for algebras over this thing? Let A be a finite dimensional associative algebra over the field F, finite extension of a function field. Here FQ denotes the finite field of Q elements. We address the problem of computing the Jacobson radical and the problem of computing the minimal ideals of the radical free part. The algebra A is given by structure constants. We give algorithms to find these structural components. Our methods run in polynomial time if M is constant. In particular, in the case M is 1. Actually, this is kind of interesting, right? So the algebra A is given by structure constants over F, and F is given by structure constants over such function fields. We give algorithms to find these structural components of A. Yeah, so I'm kind of curious about what... Okay, suppose that A is a finite dimensional semi-simple algebra, then A can be expressed as a direct sum of simple algebras. Moreover, each AI is isomorphic to a full matrix algebra, where Fi is not necessarily commutative extension field of F. And so what is the claim here? Is it that you can also compute Ni? Before turning to algorithms, we have to specify the input of the algorithmic questions considered. An algebra can be given by a collection of structure constants. In this paper, an algebra is considered to be given as a collection of structure constants. The basis is called the a priori basis of A. The algorithmic problems of computing the radical, and if A is semi-simple, the minimal ideals, the Wedderburn decomposition of A, where the ground field F is either finite or algebraic field, has been studied extensively. The methods of computing the radical are deterministic. Our aim is to extend these results to the function field case. For this reason, we work in ladder, more general setting, blah, 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 blah. In this case, radical of A can be computed by a deterministic algorithm whose complexity is... It's great that it's computable. To be more precise, we give a deterministic reduction from the problem of finding the minimal ideal of A to the task of factoring at most this many polynomials of degree not considering, to be more precise, we give a deterministic reduction From the problem of finding minimal ideals to the task of factoring out most nk log q polynomials of degree not exceeding nk over the prime field. In section 3, we describe our method for computing the Jacobson radical. The thing that I'm really curious about is if whether or not you can determine what the NI is, right? I mean, that's like the whole question in my mind. Like if you can give a presentation for these FIs, the division algebra, and then also if you can determine the NI, that's like the whole thing that I want to know. And I'd be cool with changing kind of like the whole central simple algebra package to just doing this algorithm, honestly. It's almost like, it's actually, yeah, I mean, I would be cool with that. I don't know. So okay, let A be an n-dimensional commutative separable algebra. Wait, that wasn't what I was expecting. Okay, let's just take it for the moment. So let's say we have a commutative separable algebra over the field F. Assume that the structure constants with respect to the basis are from this and their heights are limited by some delta. Then any idempotent lies in the FQ space where D is the discriminant. Can I see that being useful? Common multiple of the denominators of the exponents is also exhibited. Yeah, I still can't really get. I mean, so I really can't get behind this to some extent. Like, let's go back to this one and just see what the claim is. In 2730, this type of method is studied. Furthermore, these types of methods should work equally well for functional field. Subalgebra is not necessarily blah blah. The disadvantage of these methods is that they're based on explicit calculations and reductions finding non-trivial zeros of quadratic forms, which do not easily generalize. Wait, this can be leveraged by to compute zero divisors in A. Okay, there's a bunch of things we have to figure out. So one is that
one thing that I'm actually really confused about is that the method of this paper for finding the Vedderburn decomposition. Okay, so the thing that I think is believable is that you can maybe find idempotents that separate out the simple algebras. What would you call this? Two-sided idempotents, maybe? The thing that's not so believable is that you can find just like arbitrary idempotents. At least it's not so believable to me, because that really does say that in this case there's an algorithm for computing the index. And I'm curious about that just because, like, one thing that I want to do right at the end of the day is like just write down a bunch of examples of simple algebras and then try to compute their indices and their exponents. So let's try to see decomposition of algebras. So first off, let's just read the math side of the thing. The paper under review considers the problem constructing explicit isomorphism between two isomorphic quaternion algebras, as is well known. This reduces to the problem of finding explicit isomorphism, A tensor B op to M16 of K, that is, an explicit splitting of the K algebra. The main results are, in the case of function field, there exists a randomized polynomial time for determining this algorithm. While previous algorithms could solve this problem, such complexity could only be achieved in the case that the discriminant of K was bounded. What is capital K here? Quadratic global field. The main idea is to replace the search for an isomorphism C with the matrix thing by search for central simple K subalgebras isomorphic to the matrix ring, thus reducing the degree of the field. For this step, which uses co-restriction of algebras, it exploited that C has this form A tensor B op, and thus is endowed naturally with certain involutions. The problem for central simple K algebras is then solved using known algorithms. The paper contains also some algorithms for co-restriction algebras and orders, including an improved algorithm for finding maximal orders, which may be of independent interest. Okay, and the one that I was curious about was this one. So, extending earlier results, the authors consider algorithmic questions connected with the determination of the structure of a finite dimensional associative algebra over field F. Here, F is a finite extension of the function field. Again, the radical of A is calculated with the help of trace functions. The calculation of the Vedderburn decomposition of a semi-simple algebra A for small primes P is analogous to Berlecamp's reduction method for factoring polynomials over finite fields. For larger primes, a certain idempotent lifting technique is employed. That is not so helpful. You don't like when you see something like, you know, you're trying to ask like, oh, is there an algorithm for doing this? Is there an algorithm for doing that? And then you see a paper that says that there's some system that they make based on the hardness of problems related to this area. Deciding finiteness for matrix semigroups over function fields over finite fields. A note on the paper, deciding finiteness for matrix groups. Computing the bound of an OR polynomial. Applications to factorization. Note on locality of algebras. So what's this one? Can I not access the PDF for this one? Let K be an algebraic number field of degree D and discriminant delta over Q. Let A be an associative algebra over K given by the structure constants. And such that A is isomorphic to the matrix algebra for some n. Suppose that D, N, and the discriminant are bounded. In a previous paper, a polynomial time FF algorithm is given to construct explicitly an isomorphism. Here we simplify and improve this algorithm. If I control W, it just closes one tab. Cool. Okay. Okay, so we're really interested in this paper at the moment. And what we're curious in is what they mean when they say they find the Vedderburn decomposition. The algorithmic problems, Vedderburn, the methods, computed random. However, the methods are over finding that uses randomization. So section 4 is the one that uses, okay. In this section, we give a reduction problem of decomposing a finite dimensional sum of simple algebra over a finite extension of the field into a direct sum of simple algebras. So it's not clear yet. It's not clear reducing the problem. I mean, it's not clear. Yeah, it's just not clear. The main idea is to find central idempotency. Yeah, that's the issue. And a factor algebra modulo small irreducible polynomials. Lift them to idempotence modulo sufficiently large power, and then find zero divisors of reasonable height. Okay, let's think at the moment. Can we come up with some... can we come up with some ideas that allow us to find idempotence for algebras over such fields? Yeah, so the best hope that I would have for trying to compute the index of algebras over such fields would be to use, I mean, Brussels techniques, I think. Basically complete this field extension at some finite number of, I don't know, transcendental guys. And then try to use Brussels algorithm to directly compute the index via those Fathians that he has defined for some group theoretic Fathians. I don't know if there's any other way that seems even close to reasonable. And it's interesting to me that, I mean, basically, right, there's no idealistic way that you can compare these things. Like if you have an algebra, then you take, let's say you have an algebra over a function field, so some finite extension of let's say this field here, which is, you know, rational function field over FQ. So we've got a finite extension of that. And if I just pick some, so if I can pick like a smooth model of this function field, some regular model maybe, and pick a point on that regular model, some regular point. It has some system of parameters of the right size, and then I could complete that system of parameters. What am I doing in this process, right? So I'm taking my algebra over the function field, and it embeds, the function field embeds into the completion. But how would you say that it embeds? So the function field embeds into the completion, so the algebra extends. You can pull it back to the completion. But the way that seems to work maybe is something like you take your algebra, you extend it to some asymptotic algebra, which it's potentially ramified. I want to say you take your algebra, extend it over some open. You pick a point in the open, and then you complete, which is like you take your asymptotic algebra and you restrict to kind of like a formal completion of that point. I don't see any reason why that should preserve anything to do with the index in general. So does that just mean that we're stuck? It's probably easier also to get this algorithm working for finite fields than it is to get them working for complex function fields. But you could maybe implement Brussels algorithm for finite fields and rational function fields. Function fields over the rational numbers. Is that what we're going to end up doing? The isomorphism problem is an interesting I think that's an interesting question. That doesn't really seem to admit any immediate solutions. Here's a paper, just simple algebras are difficult. Let's try looking up Wadsworth's book. So what is that book called? Pretty sure I have it. Adrian Wadsworth. He's got a book on algebras, and it's like the only one that I actually think contains very concrete examples of very complicated things. It's in a direction that is kind of surprising. I mean, I think it's on valuations. And I swear I have it. Okay, so it's apparently this one. Yeah. Okay. So, value functions on simple algebras. So do we need to look at the premise of the book? So the theory of finite dimensional division algebras witnessed several breakthroughs in the latter decades of the 20th century. Important advances such as Adminster's construction of non-cross product division algebras and Platonov's solution to the Tanaka-Artin problem relied on inventive use of valuation theory applied in the context of non-commutative rings. Subsequent development of valuation theory for finite dimensional division algebras led to significant simplifications of the initial results and to a host of new constructions of division algebras satisfying various conditions, which shed much light on the structure of these algebras. In this research area, valuation theory has become a standard tool for which this book is intended to provide a useful reference. The theory of valuation rings has been extended to division algebras in several ways. The material in this book can be roughly divided into 3 parts, which we briefly outline below, referring to the introduction of each chapter for additional information. So the first part consists of chapters 1 to 4. They lay the groundwork for the theory of valuations on finite dimensional division algebras and its extension to the theory of gauges on finite dimensional semi-simple algebras. The second part, comprising of chapters 5 through 7, addresses various topics related to the Broward group of valued fields. Valued fields, huh? We first discuss graded field extensions in chapter 5 and review properties of valued field extensions from the perspective of their associated graded field extensions. Broward groups of graded fields and of valued fields form the subject of chapter 6, valuation theoretic properties, define an ascending sequence of 3 subgroups of the Broward group of a valued field. We use gauges to relate these subgroups to corresponding subgroups of the Broward group of the graded field. The main results of this part of the book yields for a Henselian field F a canonical index preserving isomorphism, mapping the Broward class of a tame division algebra to the Broward class of the graded division algebra. We can then easily read off information about the pieces from the corresponding data. The inertial or unramified part of the Broward group is canonically isomorphic to the Broward group of the residue field. The inertially split part, something. When the base field is Henselian, the properties of such algebras can be read off from the extension of the value groups with the help of canonical alternating pairing, which values in the group of roots of unity of the residue field. Since totally ramified division algebras arise only when the value group has rank at least 2, such algebras have been relatively less studied in the literature. Okay, in the third part of the book, chapters 8 to 12, we apply the preceding results to investigate the structure of division algebras over Henselian fields specifically. And we present several applications following the same methodology as in the previous chapters. In chapter 8, we first consider the structure of graded division algebras. We then derive corresponding structure theorems for division algebra, Henselian fields by relating the algebra to its associated graded. We thereby recover easily several results that have been previously established by much more complicated methods. Historically, a primary application of evaluation theory has been in the construction of significant examples. Our last 4 chapters are devoted to the presentation of such examples. In chapter 9, we obtain information on the maximal subfields and splitting fields of valued division algebras and construct non-cyclic division algebras with pure maximal subfields, non-cyclic p-algebras, non-cross product algebras. Examples of division algebras that do not decompose into tensor products of proper subalgebras are given. We show that if D is a division algebra tamely ramified over an Henselian field, then the reduced Whitehead group agrees with the reduced Whitehead group of the associated graded. This leads to quick proofs for many formulas. Finally, we give in chapter 12 modified version of the recent results of Merkuriev and Beck Merkuriev using Merkuriev using valuation theory to obtain lower bounds on the essential dimension of central subalgebras of a given degree and exponent. The assumed background for this book is acquaintance with classical theory of central subalgebras based on knowledge of the valuation theory of fields as given Bourbaki. So why are we looking at this book? The reason that we're looking at this book is to see if there's anything in here that could apply more generally than the situation that we're already thinking about. It's kind of interesting, these gauges. I can't remember. I think that the gauges are like basically like if you have a symbol algebra. I actually don't want to say it. No, it's not a gauge. Sorry. I'm thinking of armatures. The armatures on a symbol algebra or like essential symbol algebra are kind of like things that are in correspondence with like n torsion points of an elliptic curve. So it's kind of interesting. There's some connection here, which is like totally not clear. Yeah. So the questions that I think should be asked are like, really what is preventing us from doing algorithmic analysis of central simple algebras over function fields? There's one more thing that I was thinking about. So in my books, we're going to look up the Gilles Samueli book. And we're going to go to Fadiv exact sequence. It might be 2Ds. So there is this exact sequence which allows you to talk about the Brouwer group. So if we were just looking at the Brouwer group of like, let's say, I mean, so this is for K is function field and is a rational function field in one variable, so it's just like K adjoin T. And something that you can do is like some induction. So like if you want to look at K adjoin n variables, then you can try to do kind of K adjoin n minus 1 variables, and then here's the function field, one variable over that. I don't think anything about this requires that the little k is algebraically closed. And some people have been doing this. I saw. So, how is this helpful? How is this helpful? So, there's a chance that we could actually use this to compute the exponent of an algebra given to us over the function field. If we could determine, so like, let's say that we have an algebra which is a product of symbols over this some iterated rational function field. Then what we could try to do is we could try to so we could compute the residues, I think, just from the symbols, and then we could compute explicitly
There's a chance that we could compute explicitly the ramification. So these cyclic extensions, we could compute the order of these cyclic extensions. In which case, taking like the LCM would give us the exponent of the image. And then I think there's a way to kind of construct like an algebra whose Brouwer class would also have those things, and the difference would give you something in the Brouwer group of the base or of this little k. If you could do that inductively, then you could figure out the exponent of the algebra that you started with. Is that true? That might be true. So there's the question of yeah, so there's a question there, which is that how does this residue map look explicitly? But I'm pretty sure if you already have a presentation in terms of a sum of symbols, then the residue map is just explicitly determined by this kind of formula. Okay, I was thinking that they had a Fadiv sequence also written down in that chapter, but maybe I missed it. Oh, maybe this is just it right here. This is roughly the thing that I was thinking about. So this is probably exactly what I was thinking about. So basically, you have a bunch of symbols, then you can take them to their Galois symbol, and the residue map is given to you explicitly in terms of what these boundaries are. And so the only thing that you need for that is, I think, to be able to compute valuations. I don't think you should have to figure out what the valuations are at every point. Is that true? I think it would be nice, and I think it's probably true, that there's only so many points that you need to check the valuations for. And how would you determine? One second.